Welcome everybody to another episode of the I Am All Ears podcast. My name is Rohit and I'm here with Sushant and Shrujal. Today we have one of my friends from school who's now an astrophysicist or soon going to be a doctorate in astrophysicist in Germany. His name is Prajwal. He's an alumnus of Kumarans, which is where we both met. We studied from grade 8 to grade 10 together. He pursued a master's in physics from BITS Pilani in India, and after working as a research assistant in the Raman Research Institute in Bangalore and also at the Inter-University Center for Astronomy and Astrophysics in Pune, he's currently pursuing his PhD at the Max Planck Institute for Radio Astronomy in Bonn. His area of research is related to neutron stars called Pulsars, which are known to show some really bizarre physical properties. So, welcome on the show. Thank you for coming all the way to Aachen.
The honor is mine. I'm very grateful that you thought I'm worthy of this. That you'd like to interview me. I mean, the first time you told me that you want to speak with me about this, I really liked the idea and I thought, why not? I should give it a shot. And I'm really glad to.
Just be prepared that you might go viral.
Well, if I wanted to go viral, I wouldn't be doing astrophysics.
You never know.
And I don't know, after Big Bang Theory, people might...
Maybe.
There's always the hope.
Yes, there's always hope, but
All right, so let's start with... how were you interested in astrophysics in the first place?
To be very honest, I think up to my class 12, I was interested in physics and biology, but then I decided to take up physics because I thought that's what interests me more, and physics as a subject itself I feel is more wholesome, which is what I felt at that time. And that's why I decided to do a master's in physics. I didn't want to just pursue engineering like most of how people, most of the students.
Yeah.
I'm not going against it. It's just that it was not my cup of tea that I just pursue engineering because I had an interest for science. But what happened was, I also realized that engineering has its own pros. I mean, there are a lot of interesting things in engineering as well, which could be useful, and which I don't regret right now. There are some things I feel, even if you're in research, it's better to be an engineer. Better to come from an engineering background. It's possible. So, there was this dual degree course in BITS Pilani, where they offered science and engineering, where I could do a 5-year course with an MSc in physics, as well as get a bachelor's in electronics. So that really interested me. And what happened is, as I pursued this course in my second year, we were supposed to do a compulsory summer internship, and I was very lucky to get this opportunity. In the Indian University Center for Astronomy and Astrophysics, which the acronym is just pronounced as IUCAA. It's one of the top astronomy institutes in India, started by a very famous astrophysicist, Jayant Narlikar. And I got the opportunity to go there, and this is the first time I was exposed to any kind of research at all in my career. So all this time I was just doing coursework, just finishing courses, studying for exams, just typical things you would do when you're pursuing engineering or even science. I mean, just sticking to the coursework. But this was the first time I got an exposure to something different. And I really liked that experience. It was not easy, but it took some time for me to get adjusted with things as to how these things work. How it is in research, what are the things you're supposed to take care of, what you're not supposed to do. All this took some time. It took me. I was there for about 2 months, but it was a very humbling experience. there were some lectures given by very famous scientists there, and I didn't understand anything. But I used to note down the keywords, whatever they would say, and just Google them back and just try to understand things on my own. And it was a very nice experience. And that's what got me into astronomy at first. It was the first exposure I had with astronomy. And yeah.
Where is this institute?
This is in Pune. So the University of Pune, it's actually a huge campus. It's somewhere in the middle of somewhere close to Ganeshkhand in Pune. For people from Pune, maybe they would be familiar with this. The building is within the University of Pune itself. So the campus is actually within the University of Pune. And apart from IUCAA, there is also the National Center for Radio Astrophysics, which is a neighboring institute right next to it. And I had done my final year project there, actually. So they're actually neighboring institutes. It's like, I don't know if this is the only comparison which comes to my mind, which is MIT and Harvard, because they're right next to each other. So it's similar here as well. They're actually right opposite each other. So, yeah.
How long was your summer internship?
The internship was, so I think I started somewhere around mid of May and ended around third week of July. So it was about more than 2 months.
Okay.
So it was a summer internship, and you don't expect to learn too much from it, but it's at least some kind of exposure. So that's the good thing.
So before you went to Pune, what were you expecting, and what did you get in reality?
It's very funny. Yeah. Okay. About that, I think there was some point in my second year, starting of my second year, where I thought I will do string theory.
Okay.
Yeah.
Hey, why are we laughing? It's possible.
Okay. No, you can laugh. You can laugh.
Second year of your bachelor's.
Second year of my this was an integrated master's. What I did.
Yeah.
So yeah.
5-year course.
It was a 5-year course. So second year of my course. There was at some point I thought I'm going to do string theory. I went and spoke to a prof saying what should I do for string theory, and he kind of, I think he was laughing inside, but he didn't laugh at me. But
You know it feels wrong.
but he told me some things that it's not easy. You need to do a lot of things. You need to be really good at math. I mean, he didn't tell me that, but then I realized that later, and I realized I liked math, but the kind of math we did in up to 12th was actually nothing. And then you get exposed to this crazy abstract math, and then you realize that, okay, this is not really for me, which is what happened to me. But string theory is completely about abstract math. There's definitely a lot of physics, but if you want to do cutting edge research in it, you need a very good foundation in math. So I realized quickly that this is not for me, and then I realized that I probably like something more hands-on and maybe something more experimental. So I did do an informal project in my second year, but this was something completely different. I was working with lasers, trying to set up an interferometer, just to get some exposure to doing something different from coursework. It was nothing great came out of it, but it was just some kind of an exposure again, so that I could do something outside coursework. Yeah.
And so when you started in Pune,
Yes.
you encountered a totally different.
Yes, I then exactly. When I started in Pune, one thing was that I realized how dumb I am.
I think every millennial goes through that when we start working. So.
Yeah, because the people kind of throwing jargon terms, like crazy terms, as if it's something very obvious you're supposed to know. And I had no idea what they're talking about. And the other thing was that I was just telling Rohit on the way where I was coming that I didn't particularly like programming.
Okay.
And and I didn't pursue computer science in my +2. I took biology. And there was a reason. The reason why I took biology was more of elimination. I didn't like computer science.
Okay.
And I think the other option was economics, which I was not really keen on. And biology was okay. I was okay with biology. I didn't have any grudge against it, if you can say that. But what happened was, I realized as soon as I came into IUCAA that I'm supposed to program. And it was not easy. Realizing that.
Still not.
And luckily the language I had to use was not something like C or C++, it was MATLAB, which is still not really a programming language because functions are written for it. You can call functions and you can just get away with things. But still that mindset of trying to program, debug, I didn't like it a lot. I had a course in my first year as well, which I didn't particularly like it much, and it just made it worse for me. I thought this is the time maybe I'll start liking computer science, but it didn't happen. But then eventually I got the opportunity where I had to program, and it was difficult, but then eventually I caught up with it, and even now, every day I've been learning something new in programming. I think people who program realize this, that you're always learning something or the other.
Yeah. Especially if you use Linux.
Exactly.
You have to Google to Stack Exchange to figure out.
Exactly. I have so much respect for the people in Stack Overflow.
What in my master thesis, in the acknowledgement section, I have actually acknowledged Stack Overflow on my community. Without
totally.
them, this won't be possible.
Totally. Yeah, so at that point, it became more about... So usually how it works, at least it worked in my internship, was... I think the first few weeks I just studied about the subject itself, trying to understand the subject, and then it was all about just programming it. Like, you have a problem, this is what you want to achieve, and you just program the hell out of it. That's it. Which is what I'm doing for my PhD as well now. So it's just that I don't know where it's going, but but that's how it is in research.
People ask me this question very often, like, why do mechanical engineers need to program?
Okay.
It's like a calculator.
Yeah, exactly.
It's a new calculator. That's all it is.
Exactly, yeah. It's a tool. I mean, this is how I think of it, and this is what my mom also tells the same thing to me, that she's a computer science teacher in plus 2. So she's a computer science teacher, and I still didn't want to take computer science. So you imagine how much I hated computer science. So she also says this, that you should be lucky that you're using programming as a tool for your research, because many people who just pursue computer science are just getting instructions from their clients that they want this, and they're just doing it for them. And they're not really being very creative about things. But then here we are thinking of our own problems, we are doing our own things, and it's very flexible, very customized to our problem, and then you program basically very specific to what your problem is. So it's the good thing is you're also scientifically thinking a lot, and you're also learning programming at the same time. So it's a bonus. Yeah.
So do physicists treat mathematicians as tools?
I would actually... It would also be the reverse case, right? Like almost like...
Yes, I think both of them have a grudge against each other. Which is expected as well. But I personally have a lot of respect for mathematicians, especially for people who are doing pure math. Because I think it's something...
They set the language.
Exactly. They're completely shooting in the dark, and they have no idea what they're coming up with. And eventually, 100 years down the road, it's going to find an application, which is what happened with Einstein as well. With some theories which were developed in non-Euclidean geometry, for example, and eventually found its application when Einstein had to formulate his theory of general relativity. All this math came into application. So you never know. This is why. So after that story of Einstein and a few other things, I realized that it's very important that there is, of course, computer science. It's a machine, so there are limitations. But this is where things like quantum computing can change things, of course. But math is definitely. I have a lot of respect for it. I can't do it, but I have a lot of respect for mathematicians.
I just want to borrow Srujal's question
Yes.
from something, but I feel is more appropriate
Sure,
now.
sure.
So, what would you say is the difference between astronomy, astrophysics, and cosmology? For someone who's like not
That's a very
completely
good.
new.
That's a very good question. That's a very good question for people who are very new. I'm very. The good thing is that I want to compliment you that you know that all three are different.
Actually, I borrowed
Because-
this question from Stack Overflow.
Oh, okay. I have to take back my words then. Okay, because but the other good thing is that you didn't ask me. Is it the same as astrology?
I was telling them.
Can you read my palm?
I have not been asked that, but I know people who have been asked that. So
Okay.
luckily, I haven't been asked
Yeah,
that.
I was telling them. I was telling Sujal today morning that on Reddit I saw this video clip from The Bachelorette, and one of the bachelors was an astrophysicist, and he walks in and he introduces himself to the girl and he says, "Hi, my name is this, and I'm an astrophysicist." And she says, "Hi, oh, I'm a Libra," and he's like, "Nope, that's done."
Yeah. That's definitely not. So coming back to your question, astronomy, astrophysics, and cosmology. So astronomy is the study is more to do with just observing space or observing objects in space. For example, let's say you have a telescope and you have like a basic optical telescope and you point it to, let's say, the moon, and you're observing it, and let's say you're trying to understand if there's any variation in the brightness of the moon or something like that. Or more than that, let's say you are looking for a comet. You know that it's going to come at some point of time, and then you point your telescope to a certain point, and then you're observing things and you're waiting, and it comes, and you make some records saying that at this point you saw this particular comet, at this point it was so and so. You make some kind of sketch maybe, or you maybe take a photograph. So what is happening here is you're collecting data, you're observing things. This is what astronomy is about. But you're not trying to explain why you see it. This is where astrophysics comes. So astrophysics, you're trying to use physics to explain why you see those things you observed. So astronomy is about collecting things, making observations about space, about different objects, which is what happened in the 1600s when Galileo made his telescope and he pointed to the Jupiter and its moons. Basically, in fact, even before that, it was there was this famous Danish astronomer called Tycho Brahe. So he had made some observations, and in fact, using his data, Kepler came up with his laws of motion. So Kepler, of course, is credited with the laws of motion, but he used the data which Tycho Brahe observed rigorously. So he tracked movements of many objects over, basically the planets over several days as to where they appear in the sky. He made a rigorous record of things. So this, as an astronomer, this is what he did. But then Kepler came up with the physics as to why we see these things. He came up with the laws of motion. So he was more of an astrophysicist. So this is how usually you differentiate astronomy and astrophysics. Cosmology. Cosmology is a very new topic in astronomy, to be honest. So it's only about 100 years old. What happened was when Einstein came up with his theory of general relativity, he came up with these equations called the Einstein's field equations. And then he realized that his equations tends to make... he didn't like his equations because it said that the universe is expanding, which he didn't like. So for him personally, he thought that the universe is something which is stagnant. It doesn't vary with time. It's just stable. It can't be expanding and things. So this is where Einstein went slightly off from his scientific mentality, and because personally he just thought that the universe is stagnant, it cannot be expanding and those things. So I won't get into the details of this. It's a very interesting story, but I would definitely recommend you to look into it. But this is how cosmology began, by first thinking about how the universe itself came into being. So I'm sure you have heard of this term Big Bang and all these things. So this came much later in the 60s. So one of the things why Big Bang became popular was, the theory became popular, much popular, was the discovery of the CMBR, which was the cosmic microwave background radiation. So what happened was, even now with, let's say your old television with the antennas, about 3% of the signal is actually the cosmic microwave background. It's all around us, basically. It's this radiation which is emitted in microwaves. It was the radiation which came from what you'll now say as the Big Bang, which started the universe. That's how people say it. So it's this remnant of the radiation which comes from there. And now it's traveled through space and time for so long, it's lost energy, and now that's why it's in microwaves. That's why it's now in microwaves. So you can't really see it, but you can sense it in the microwave region. So cosmology is the study of how the universe came into being specifically. Why are things like this? And of course, there are all these different theories about multiverses, other different universes. Also, you're trying to explain basically everything which exists in the universe, why it came into being, what are the initial conditions which led to all this to happen. That's what cosmology is about.
Is Big Bang theory, is it like, are we like 100% sure that's the thing? Or it's like the best version we have so far?
Exactly. It's the best known theory because many observational evidences point to definitely a start.
Okay.
So there's some kind of a start. But again, Big Bang is a very general term. We know that there was some kind of a singularity where basically it started from something like literally a singularity. That's what we call it. And then there were some processes which happened. So there are these terms called inflation, where there was a sudden expansion of things, and then after that the universe cooled down a bit. There was stars started forming, galaxies started forming, and all these things. There are these theories which support this, and there's also observations which support this. And that's why we have some kind of an idea how things went, but there are still gaps in between which we still can't explain. And this is what cosmology is trying to do, trying to explain these gaps. And of course, there are many conflicting theories. There are people who still believe, in fact, the one I mentioned, Jayant Narlikar, who started IUCAA in Pune, he's still a firm believer of the steady state cosmology. So steady state cosmology, basically, people who believe that the universe is not expanding or contracting. It's just the same. And just to add on to that, in 2011, the Nobel Prize was given to Brian Schmidt and others for proving that the universe is not only expanding, but it's actually accelerating. So the expansion is actually accelerating. So there's something which is driving the universe, which is making it expand. From basic physics, we know that gravity is trying to attract things, but there's some kind of crazy thing which is trying to push away things in the universe. And this is what we call dark energy. Yeah. So, and we believe that is about 76% of everything in the universe is dark energy.
76?
Yeah.
How do you come up with that?
That's a good question. This is just to do with... these are again all observations.
Is it a statistical observation?
It's basically all statistical observations. It's a bit based on simulations. So actually it's heavily based on simulations. You try to explain what you see in the universe using some models. And what you do is you kind of try to fit percentages for dark matter, dark energy, actual matter, everything. And then there is this one particular combination which does very well with observations so far.
Okay.
Yeah, so it's basically trying to fit the observations with theory. This happens all the time in any kind of research.
So coming to like, what are you working on? Maybe just before that was like, what is a typical day for an astrophysicist look like?
Okay, so
because I'm sure it sounds super cool, but I think the day-to-day reality.
So one thing I'll tell you is we don't work in the night only. if that's what people think. Because maybe people might be thinking, okay, you go outside, you set up the telescope, you look at the stars. It's not like that.
That's astronomy.
Yeah, exactly. That's astronomy. So as an astrophysicist, I am basically, my work is writing software for astronomy, for doing astronomical data analysis. So a typical day for me goes like, I come around 10 o'clock to my office to work. I check my mails, and then basically I start working on one of the problems that I've had. So basically, one of the problems is basically I go to a particular program and I'm trying to debug why it's not working. So on a daily basis, to be honest, I'm just debugging programs, attending meetings, helping some of the new students maybe who have doubts, trying to figure out things as to why my code is not working. And then once, let's say, I get some plots, I try to understand why the plot is like this. Is this what I expect from the plot? Based on what theories we know, should I expect something else? And in case I find something else interesting, then I kind of try and go and report it to my supervisor that, hey, something looks interesting here. And then he might come up with some feedback as to what's happening, and then we have a discussion about it. So this is how typically a day goes. Also, not me, but a lot of them just take a lot of coffee breaks. I'm not a big coffee lover like the others, but yeah, coffee is one thing which is very integral with astronomers, I have found, at least most of them. Also, we are not really producing fancy images like what you see in the internet. Of course, there are people who do that, but we are, as a research group, we have a lot of collaborative work. We have collaborators from different continents. So sometimes we even Skype with those people. We just want to get updates about what things are with a certain project, for example. So particularly one of the projects I am working on, there's a telescope being set up in South Africa. It's already set up actually. It's called the meerkat, which is named after the animal meerkat in South Africa. So it's just started operating, and it's starting to take some data, and I've tried benchmarking my software pipeline to try and see how well I'm able to analyze the data which comes from this telescope. And this is actually a collaborative effort. There are people involved from Manchester in the UK, there are people involved from the US, Virginia in the US, people involved from Melbourne in Australia. So it's pretty much the entire spectrum. So yeah, this is how particularly it is with my group. And yeah, that's how usually a day goes for me.
What are you working on?
Also, I am doing multiple things. So one thing I'm doing is, as I said, I'm trying to search for these very interesting objects called pulsars. From people from India would know pulsar in a different from a different point of view. It's not the Bajaj Pulsar. It's not the Bajaj Pulsar motorbike.
I own a Pulsar.
So, but it's so. There's a very interesting story. Maybe I should tell this story because it's my field. I think I should try to propagate this story. So, around 1967. Okay, maybe let me start with one thing that telescopes in general, you would be familiar with optical telescopes where you have telescopes and you would look in the sky and then you would have an eyepiece. Also, there are these massive, huge mirrors sometimes they make, and you collect data on a CCD, on a charge-coupled device, and then you try to make an image out of it. But the interesting thing is astronomical objects emit in multiple wavelengths. So they emit even in radio. So typically you can use your satellite dish and point it to the sky, and you can actually detect the sun in radio. You can detect the center of the galaxy in radio. And there are many objects in the radio sky which you can detect with just a radio telescope. And the radio telescope is basically like your TV antenna dish. So I particularly work with radio telescopes. And what happened was radio astronomy itself. So that's why radio astronomy is basically studying astronomical objects in the radio spectrum. This field is very new compared to other fields in astronomy. And it started only in the 40s. And what happened is, so after the World War, there were a lot of dishes which were used, of course, for radar, which were not being used anymore. And people started using them for radio astronomy. So it became a trend. Many people set up these dishes, and they were observing molecules in space in the radio. So astrochemistry is also a very interesting topic. So I don't work on that, but I'm just saying that there's a very interesting things that you can do with radio astronomy. Now with my topic, what happened is in the 60s, just like others who are setting up, in I think this was in Jodrell Bank. It was in the UK. It was in the UK. A graduate student, her name was Jocelyn Bell. She was working with Anthony Hewish, who was her advisor. So she was setting up a radio telescope to basically observe planetary scintillation, basically to do with trying to study planets in the radio and try to make some kind of studies. I won't get into details of it. What happened was when she set up this telescope, she started noticing these periodic signals. So she was getting these lighthouse kind of signals, basically beep, beep, beep. That's what the chart recorder recorded. And she was wondering, what is this? She was very intrigued by it, and she went to her advisor as well, and she showed it. And the first thing they thought was they found aliens. And they named the signal LGM, Little Green Men. So, and then what happened was, that was the first idea they had thought that maybe there's something interesting. They followed it up. And then when they followed it up, they realized it's an astronomical source. Because what happens is, astronomical sources don't follow solar time. They follow something called as sidereal time. So what happens is, let me not explain too much. So a very basic thing. So we know that the Earth is revolving as well as rotating, right? So it's rotating and revolving around the sun. So when the sun comes up and down, we know that it's 24 hours. But what happens is the other stars, their position is relatively going to change because we are revolving as well. And because of that change, you actually see the source the next day about 4 minutes before. So it's not 24 hours, it's 23 hours, 56 minutes. And this signal, the Little Green Men signal, actually they noticed that it was following sidereal time. That's what we say. So it's definitely an astronomical source. It's nothing to do with aliens. And then they further studied it, and I won't get into the details of it, but they studied the properties of this signal as to why it's periodic and those things, and they concluded that it's basically like a rotating lighthouse in space. So it's rotating, it's emitting these twin beams across the sky, and every time the beam sweeps across our line of sight on Earth, we're able to see a beep. And that's what is happening. So they concluded that it's a rotating star. Now there are some more analysis they had to do to exactly specify what the star is, and with some rigorous analysis they concluded that it was a neutron star. And a neutron star is basically a star made of only neutrons. So neutron is something you find in an atom, which in the nucleus. So this is a star just made of neutrons. So the kind of physics we notice here on Earth, you can't apply those physical laws on a neutron star, because this is quantum mechanics. You're dealing in the quantum mechanical regime, because it's a star made of only neutrons. So the kind of forces you have to deal with there, the kind of composition, the kind of equation, we call this the equation of state. Basically, the relation between the density of the object with the pressure is not like what we see on Earth. All these things are very different. And studying at these twin beams, just looking at these signals, we can try to make some conclusions as to what are the kind of physics which are happening there. And to be very honest, this happened in 1967, this discovery. It's been 50 years. It was 50 years 2 years back. It's 52 years now. And we still know very less about why they emit the way they do. We know that they're very strong in radio, which is why we use radio telescopes to observe these objects. And the amazing thing is, you find this in science. The more you start learning about some particular thing, the more you realize that you don't know so much. And you try to answer one question and there are 100 more questions which pop up. Why doesn't this happen? Why doesn't that happen? That's exactly how it is with pulsars. And what I'm trying to do is, one thing I missed was that in 50 years we have now found 2,700 pulsars in our galaxy.
Only in our galaxy.
The thing is, there are definitely pulsars in other galaxies, but our telescopes are not sensitive to it.
Okay.
So this is where we are limited by our technology. That we are not able to make sensitive enough telescopes that we can see, because these are very compact objects. So one very interesting thing I missed about pulsars is that the radius of this object is about 20 kilometers. It's like the radius of, I think Arkin's radius is much less. Oh, okay. It's like the radius of Arkin,
Wow.
and the mass is a little more than the sun. So,
So
it's so much which is within the radius of Arkin. So you can imagine how compact it is. So it has all these kind of bizarre properties, and
Just to interrupt.
Yes, sure.
How do you conclude that it's a neutron star?
That's
How
a
do
very
you
good
know
question. That's a very good question.
I have a smaller question. How periodic were these pulses?
Yes, that's a very good question as well. So, okay, so maybe first I'll try to answer your question. One thing is, there was a lot of theory already developed about evolution of stars, as to how stars evolve, what kind of things what kind of bizarre properties they might have, what is the life cycle of a typical star. One of the things we knew was that when a star dies, there will be something called as a supernova, which is basically this huge explosion where a lot of material is just emitted all around, because what happens is at some point the nuclear fusion process is not able to balance the self-gravity of the object.
Okay.
And at some point the nuclear fuel runs down. I mean, it is just gets over, and the self-gravity just pushes and pushes, and at some point it gets so heated up that it just blasts off, and there's something left behind always. Now there are three things which are possible that can be left behind. One is a white dwarf, which is what our sun is going to be in 5 billion years. So it's already lived over 5 billion years. Another 5 billion years later, it's going to become what is known as a red giant, and then eventually the outer layers of the sun are going to move out, and there's going to be a white dwarf left.
We are quite sure of this.
Yes.
Okay.
Because our models about evolution of stars, these are some of the standard things we first always learn through. If you want to learn about star evolution, is one of the first things we learn.
Okay.
Basically, there are some conditions. If the mass of the sun is so and so, the radius is so and so, it's going to fall in this category. If it's going to fall in this category, this is how it's going to evolve. So you can make these predictions. This has taken a lot of work, of course. A lot of objects have been observed rigorously. Basically, it's been a collective effort of astronomy and astrophysics to come to these conclusions. So there are three possibilities. One is the white dwarf. One is this, I'm sure all of you love this word and everyone keeps talking about it, which is the black hole. So that's the other possibility. The third one is the neutron star. Now what happens is, your question is slightly related to explain his question. These periodic signals which were observed were milliseconds. It's every millisecond. So it's something very fast. It's something very quick. And if they also thought it could be some kind of vibrations, but then that was also immediately ruled out. There was some again, I won't get into the details of it, but one of the explanations was that it could be a vibrating white dwarf. But then that was also immediately ruled out. It had to be something rotating, which is super fast, because if it's giving periodic signals every millisecond or every second, it has to be something. Actually, the first discovery was actually seconds. I will come to the millisecond discovery, which was made like 20 years later. So it was in something in seconds. Now, what happens is you can just calculate, let's say it's seconds, and let's say you have an object and you have a certain radius and it's emitting in seconds. That means the speed at the surface at some point will reach very close to speed of light. Does that make sense? By any chance? Okay, so let me explain it this way. Let's say an object is rotating, and at the surface...
Maybe one question before that.
Yes.
So this energy radiation is coming because of is it because of the rotation or is it because of some other process?
It's actually rotational kinetic energy.
Oh, okay. That makes sense.
Yes.
Okay.
It's like a huge generator, to be honest.
Okay.
So it has a massive magnetic field. It's about... So if you have worked with units of magnetic field in Gauss, it's 10 power 11, 10 power 12 Gauss.
Because I was thinking the sun is emitting heat and light,
Yes.
which is coming from fusion.
Yes.
So this is not the process that's in the pulsar. Okay, got it.
The pulsar is...
So that's why we can estimate the spin.
It's something very different,
Okay.
and we still don't know the exact theory for it. We don't have a complete theory for it, but we know some things. We have some clues to it. And this is what these things are. Basically, it's like a massive dynamo, which has some kind of crazy radiation. It's something close to what is known as synchrotron radiation, which is... Again, I probably won't get into details of it. It's basically if electrons are accelerating, if charged particles are accelerating along a magnetic field, they emit radiation. But this is happening at relativistic speeds. When I say relativistic, they're very close to speed of light. And when things are very close to speed of light, you have to modify your theories a bit, according to what Einstein has said. So all these things come into play, but still this doesn't completely explain things, but this is explaining some part of the story. Now, what happened was, because we are getting these signals in every second, what happens is, if the radius of this object is, let's say, 1,000 kilometers, it turns out that if you get a signal every second, you can work out the math. That means at the surface, you will have a speed much greater than the speed of light, which is not possible. So it has to be a compact enough object which falls within that second range. So that's how it was concluded that it was a neutron star. Because neutron stars, we know that they have a certain radius and which falls well within what the periodicity we see with these signals.
Could it be that the speed of light is the limiting factor in the star formation? Because it cannot go faster than the speed of light?
So this is a remnant of a star which has exploded.
Okay.
Yeah. So star evolution is a different thing. It's just to do with basic balancing two forces, basically. The self-gravity of the object and the fact that there's nuclear fuel which is causing fusion.
Okay.
That's it. It's just a balance between those two. That lasts for years. At some point the fuel is going to run out. And then... you're going to...
The expansive force of fusion is just the nuclear process that is pushing out...
Exactly.
Like the
It's
helium or
pushing out
something.
materials. Exactly.
Okay.
It's just pushing out material.
Okay. So the kinetic energy of the resulting thing from...
Exactly.
Okay. Gotcha. Yeah.
And how did you conclude that the mass of the neutron star is so much higher than the sun for its diameter?
Okay, that's a very good question again. So this comes from quantum mechanics.
Okay.
So you know that it's a star made of only neutrons. You have some idea of what the mass of the neutron is. You have some idea of what the radius is. So you can come up with some estimate as to what is the mass. But again, this is a hot topic of research. We still don't know for sure what the neutron star is made of. And since we don't know what exactly the neutron star is made of, we can't really conclusively say what is the mass. We know from observations that the mass of the pulsar is somewhere within this range, But then if we really want to know things, we need to calculate things like the moment of inertia of the star. And these things there's a satellite now launched by NASA, which is called NICER, which is basically trying to do this. It's trying to observe some of these pulsars for a long time, trying to come up with an estimate for the moment of inertia, which will give us some idea of the mass, and that will give us some idea as to what is the equation of state of what is this neutron star made up of. The interesting thing is the neutron star is not only made of neutrons, it's made of neutrons. It's a sea of neutrons made of some protons and electrons. It could also, the core of it could be quarks. We're not sure.
Oh wow, okay.
Again, there are all these bizarre theories. There are a lot of theories. And what we're trying to do is, from observations, we're trying to rule out these theories. So sometimes we observe something. There are some observations done. We have calculations to say that the mass is probably in this range. And once we see the mass is in this range, there are some theories which say they are in some other range. You rule out those theories. Those theories are not anymore. But there are still enough theories that we still don't have a conclusive answer for it.
And the white dwarf can become another sun.
No, the white dwarf just stays on. It's basically a star made of electrons. That's how you can think of it.
Okay.
So again, this is quantum mechanics. So there's something called as the electron degeneracy pressure, which basically it's to do with the fact that in quantum mechanics you would have learnt about these levels which each particle can fill. So at some point, the electrons fill all the levels, and then you're not able to fill any more, and that is kind of counteracting with the gravity. And that's what happens in a white dwarf. So what happens is, when a supernova happens, at some point the quantum mechanics takes over, and quantum mechanics also has a limit, because all electrons will start occupying all the states, and at some point it will reach the brim, and if some other electrons try to come into that state, it's not able to. So that is where electron degeneracy pressure takes over, and that is able to balance out gravity, and that's what happens in a white dwarf. And that's just going to live on for many years. It's going to radiate.
It's stable.
Yes, it's kind of stable. Again, this is something I'm not completely sure of, but some people say it might just become black. Becoming black as in it's going to radiate and eventually just going to lose energy, but it's on the time scale of several million years.
Okay.
So again, this is, I have to be very honest here, I don't know the exact details of this. But with pulsars, what happens is the mass of the progenitor star. So progenitor is basically the main star which became, which actually, on which the supernova happened and which left behind the neutron star. That has a very massive mass. So if it had a very massive mass, the gravity was also much more. So sometimes it's possible that the electron degeneracy pressure is still not enough to balance that kind of gravity. Then the neutron degeneracy pressure takes over, which is at a much lower level. And that's what happens in neutron stars. The neutron degeneracy pressure is balancing the gravity.
And even if that is not enough, it becomes a black hole.
So
there is no transition that a neutron star will become a black hole. So each
No.
I thought the culmination of every star beyond a certain mass was a black hole.
Yes, that is the theory. So this is around 20 solar mass.
Yeah, I remember some 1.44 times something.
That's the Chandrasekhar limit.
Yeah.
So that is basically a limit on the mass that a white dwarf can have.
Okay.
So he did this very simple calculation as to, again, not simple. Sorry.
There'll be a comment saying simple calculation Prajwal 2019.
No. It's sort of simple. It's a brilliant. The brilliant thing is, again, a very nice anecdote about this. He was 19 years old when he solved this problem, and he was on a ship to the UK from India. He was on the way to meet his potential advisor R.H. Fowler, whom he worked with. So it was on a ship, and he solved this problem as to, let's say the electron degeneracy pressure is so and so, and the gravity is so and so, and it turns out that from the equations, when you solve for the equation of state, it turns out that there's a limiting mass for what the white dwarf could be. Again, there's a lot of math involved in it. If you guys are interested, I can give you a link to how this calculation was done. And the one who explained this was actually a student of his. And he explains this really well. So I won't get into the details of that. So he just concluded that from the math of it, he realized that there must be a limit on what the white dwarf mass could be, and that was 1.44. That's what is called now as the Chandrasekhar limit. Yeah.
I have just one follow-up question.
Before that, just a remark that I think sometimes the simplest of things are the most brilliant.
Yes,
that
is true.
That is true.
Exactly.
Quoted this, right?
That is
simplicity is that most sophisticated.
Yes, that is true. That is true. In fact, with the kind of professors I've worked with, my favorite ones have been the ones who think very differently, not because they're coming up with bizarre ideas. It's because they're looking at things very simplistically. They look at some things, they look at certain other things, and they say, just approach the problem like this. Maybe it's like that. And it's that way of thinking which actually solves a lot of issues.
Yeah.
I mean, this is one thing I kind of don't like about astronomy nowadays, and maybe it's happening everywhere else as well, I'm not sure. Everything is becoming data-driven. And you're losing the essence for having simplistic ideas to explain things. You're just thinking about taking more data to explain things, which is, I understand it's good. Of course, we have good technology, we have things, it's nice, but it's also good to think of very original, simple ideas just from what we know. You don't always need to have data to come up with ideas.
More data means more work for astrophysicists. That's just the laziness.
Exactly, yeah. That's why the most brilliant of physicists or astrophysicists or scientists come up with these very amazing ideas, just not depending on many things. They just think of certain things, they have some kind of intuition about things, and they just say things. And
it's a brilliant guess.
Yes, it's basically a brilliant guess.
Yeah, so my follow-up question was, you said that these radiations are emitted when charged particles are revolving.
So what is actually happening is, let me explain that. So it's a huge dynamo. So think of it like a huge bar magnet which is rotating.
Yes.
It's actually like precessing. So what happens is the rotation axis is not aligned with the magnetic field axis for these pulses. So what happens is, it's not always like this. So it's basically, let's say the rotation axis is like this, and this is how the magnet is aligned, and you actually have like this. But this is how the beams are aligned. So sometimes you get part of the beam, you don't get the entire beam. If the angle between the rotation axis and the magnetic axis is 90, you're exactly able to see the beam this way. But let's say both of them are the same. Let's say the angle between the magnetic axis and the rotation axis is 0, then you'll always be able to see the beam. So this is just one thing. Now, what happens is, it's a huge dynamo. From classical electrodynamics, you can prove that if there's a huge magnetic field which is revolving, it generates a very huge electric field. So on the surface, there's a huge electric field, a huge voltage difference which is generated. This voltage difference leads to some kind of particle physics cascade reactions. So there are these electrons and positrons which are created simultaneously, and it's a cascade basically, because this potential difference is able to generate energies where neutrons and electrons are actually pushed out of the surface. And when they're pushed out of the surface, they start traveling along these magnetic field lines. Because these magnetic field lines are so strong, so you would know that from basic physics, when you have a magnetic field and you have an electron, it starts revolving around it.
Yeah.
This was the cyclotron, basically. What happens here is the magnetic field is so high that it doesn't go around it. It just follows the path. So basically, the radius of gyration, what you call, is 0. It just follows the magnetic field because it's so freaking strong that it just follows these lines. So we call this curvature radiation because it's traveling around these curved field lines. But as soon as it's traveling around curved field lines, it's accelerating. And if electrons are accelerating, they're going to emit radiation.
Okay.
So this is one of the explanations as to why you get radiation. Yes.
I thought neutron stars doesn't have any charged particles.
That's what I'm saying. It's a soup
that's-
of neutrons,
yes.
but they're also a mixture of protons and electrons.
Majority neutrons.
The majority is neutrons.
But the particles are like high enough to emit radiations.
Exactly.
Wow. I have to admit I didn't understand most of this stuff.
Well, to be honest,
but-
I don't understand a lot of things as well. I have a lot of questions about things, and many of the answers are that we just don't know.
I love this about it. It's so humbling,
Exactly, yeah.
like astrophysics. It's like it puts you in scale to the.
Yeah,
whole-
there are so many things. Even actually, there is research now about the Chandrasekhar limit that maybe it's not true. There could be stars above it.
The white dwarfs can be.
It could be more. It's a hot topic of research now. There's a particular group in my not in Max Planck, but the neighboring institute, the astronomy department of University of Bonn. So there is a star evolution group who I think some of them work on this. So yeah,
So are they astronomers or astrophysicists?
I would say astrophysicists,
Okay.
because we use physics to model these things, and we're trying to use. Basically, we do a lot of physics, general relativity. If you want to do things like cosmology, you need to be very good, well versed with general relativity, cosmology. Basically, working with differential equations. That's how it's going to be. But now, I think a lot of things have moved over to computers, even in cosmology, because you run simulations, for example. Very few are there who do pen and paper cosmology. Of course, these are the very most brilliant minds who are still doing it. But a lot of it is computer based, even in simulations.
Do you have tensors?
So I don't particularly work with tensors, but of course in cosmology, in general relativity, definitely you use a lot of tensors. You also have these things. I should advertise my field even more in this. So the interesting thing about pulsars is I told that we have found 2,700 of them, and each of them has its own story to tell. I mean, the first pulsar has its own properties. All the 2,700 pulsars have their own things. Have their own properties and their own things, and some of them have taught us more than the entire bunch of them, because they have very interesting properties. So one of the things is that there are binary pulsars. So binary, what I mean by that is there are pulsars which are orbiting another companion star or a companion object. So they're actually going around. So sometimes they're going around like that, or there are different combinations in which they're going around. So if they're going around, you can observe some kind of effects which will help us test general relativity itself. So if you recollect...
you mean like a satellite going around when you said...
No, it's not a satellite. Of course, there are planets going around it, but it's actually influenced by the orbit of another star. Basically, both of them are influencing each other. So maybe to give an example, I'm not sure if you guys are familiar with this. So the Saptarishi, the 7 stars, the Ursa Major, which is called the constellation, one of the stars is actually 2 stars. It's a binary system. Arundhati and Vasishta.
Yeah.
So married couples are supposed to look at it because they're kind of going around like this, because that is supposed to signify how relationships are supposed. Again, this is out of topic, but they're actually influencing each other.
But these are normal stars, not neutron stars.
Exactly. But the same thing happens with neutron stars as well.
Okay.
A neutron star can be orbiting a normal star. A neutron star can be orbiting a neutron star. A neutron star can be orbiting a white dwarf.
In the same way, like...
Yes, this is what I'm saying. And we have found all these systems. We have found a neutron star which is orbiting a companion star, a normal star. We have found a neutron star which is orbiting a neutron star. We have found a neutron star which is orbiting a white dwarf. But there's a Nobel Prize pending, which is we have not found a neutron star orbiting a black hole. And if we find that is the holy grail of pulsar astronomy. That's what we call it. Finding that can teach us a lot about general relativity itself. Because if you recollect, for about when Newton postulated his theory of gravity, for about 200 to 300 years, we believed that his theory is complete. But then Einstein came along and he improved the theory. What are the chances that Einstein's theory is incomplete? Very high. And we need some kind of a test bed for pushing general relativity to say that, hey, this theory really works in any conditions. And be it these kind of situations where, let's say on Earth, the kind of gravity we're dealing with is very weak field. We say it's weak. But in these kind of objects where these observative objects, you have very strong gravity, you have a lot of bizarre things happening, you can test if general relativity can explain things. And if they don't, then this is where it's a test bed for alternative theories of gravity to come into play. So there's a lot of research which can be done in alternative theories of gravity using pulsars. And it's a nice test bed for it.
Just to clarify, pulsar is not a neutron star, right? It's a different...
Pulsars are neutron stars, but all neutron stars are not pulsars.
Okay.
Yeah.
That's amazing. Maybe to change the topic slightly
yes, sure.
This thing is, how do you name objects in space and how do you orient yourself in space?
Okay,
right.
That's a nice question.
Yeah.
So we basically have a very crude system. I mean, it's not a crude system, but it's a very well thought out system. And I think this is the field of astrometry, where you're trying to precisely measure objects in the sky with some reference frame and those kind of things. So you have a set of you have a celestial coordinate system, and you have something called as the right ascension and the declination, which is the equivalent of latitude and longitude for Earth. So right ascension is your longitude and declination is your latitude. Now what happens is, depending on where you're on Earth, the same object is going to have a different right ascension and declination. So depending on where you're on Earth, you have something called as the local sidereal time, which is basically to do with the fact that you have a reference as to, you take a particular object in space and you say, at what point in my place will this object pass the highest point in the sky? And that becomes my local sidereal time. And this is going to be different for every place. And with reference to that, you start using the latitude and longitude equivalent to say that this object is here with respect to us. So it's basically a lot of trigonometric calculations to come up with where exactly this object is.
Is the origin sort of centered around Earth, or is it like some other point in the...
You have different... you can have a galactic coordinate system, which is to do with the center of the galaxy, galactic longitude, galactic latitude. It could be with respect to the celestial sphere, which is us. These are the two main things which we use.
It's similar to Cartesian and spherical coordinates.
Exactly.
Whichever is easier to represent.
I was actually thinking about this just a few days back. Is like this concept of a coordinate system. We take it for granted, But to imagine, there was actually a point where we didn't have a language for coordinate system, and I think was it Euclid or someone else must have come up with this. Let's have a coordinate. It must have been so revolutionary, to have this.
And there was a lot of rigorous work done in India as well in the 1000 to 1500 around that time. A lot of people, Bhaskara, Aryabhatta, they worked a lot on these things, trying to come up with astrometry, they were very good at predicting eclipses and basically precisely pinpointing objects as to how they're going to move around.
Do you have any theory, or do you know any theories of how they made measurements? I don't think they had telescopes.
This is a very good question. I think this will go into spirituality a bit if I start talking about this. So I personally think I have, maybe I'll say some things here which might anger a lot of astronomers. But although we demote astrology a lot, I think there are some things which science cannot explain. And just having a higher level of consciousness can probably open up things, even with respect to science. This is I believe this because scientists have this notion that they know everything. I mean, it's some of them. I'm not saying everyone, but when it comes to science itself, they have a very nice scientific bend of mind, and they think about things like in a proper way. They think about theories. They're skeptical about things. But then when it comes to a little bit of spirituality, if spirituality gets involved, they're taken aback and they say, hey, no, this is definitely not a possibility. This is definitely not a possibility. I don't like that, because then you're not really open-minded. I mean, if you really should be open-minded, then you should be open-minded to everything. The fact that a lot of our theories, even basically this Arundhati Vasishta, this was known thousands of years ago. Yeah. And we didn't have any technology or any kind of, maybe
it was equipment. Not physical.
Exactly, it was not physical. Yeah. And this is something which cannot be explained by just your cliche typical science which you have now. Yeah. It's something beyond, and I accept that there's something else, and I think this is what probably helps you open up to things which you wouldn't realize. And in India specifically, the culture has been like that, as to you always look at yourself, you go inwards, and it's been spiritually very strong for several years, and I think that has also had repercussions on every field of, let's say, science or anything else. And medicine. Yeah, Sushrutha came up with plastic surgery, like what? I don't know.
6 BC.
6 BC or something. And there are people in Australia, there's this institute in Australia which has a statue of Sushrutha, respecting him. They use some of his concepts to make things, and it's amazing. Yeah, so my thing is that it's amazing that we have really good technology now which can do things, but also I think there are dimensions of life which we can explore, which can also have impact on things we are trying to answer, which most of the scientists will hate me for saying this, but this is what...
It's a possibility.
It's a possibility, which is why I don't like completely ridiculing astrology as well. Of course, these things with horoscopes, with this weekly horoscope, that is bullshit. That I think is bullshit.
But I feel with astrology, if you can find someone who's not doing it for money,
exactly,
when he has no incentive,
exactly,
it's pure feel, and I think I feel the best astrologers also, they meditate a lot, and they have to do like some. It's an intuitive science or something.
In fact, a lot of the scriptures which are written of astrology, a lot of these people who are money-minded, they're just using these things as prescriptions to make their predictions. So they know that so for example, I don't know, the word in my language is Jatka. I mean, basically trying to come up with a horoscope, you try to see which house is the particular planet in, and that you say is going to influence something and somehow and something else. And there was this thing which I came across, which was that this is a simple thing. We know that tides on Earth happen because of moon, right? Moon influences tides. Why? And the moon could probably influence our blood as well. The moon could influence the kind of things which happen in our body. And that is just related to how we are, and that is related to how we are on, let's say, the new moon day or the full moon day. Yeah.
So, like Hindu calendar is totally based on lunar cycle.
Exactly.
Right? And there are some auspicious periods.
Exactly. So the thing is, the way it's glorified by some people, it's bloated up out of proportion, and people say wrong things, which is what is actually demeaning Hindu astronomy itself, unfortunately. And also creating a bad image for Hindu astronomy. I mean, for Indian astronomy, for example, which is not the case. I feel there's a lot of fundamental work which has happened in the past, and I'm not denying anything which has been done by others. They have also done fundamental work. But this is where it's about collecting all these things together and coming up with something. I don't like the fact that you just completely demean something, saying, "Ha, this is bullshit. This can't be possible. This is the right thing." This is what I don't like.
It could also possibly just be a natural human reaction, because if you think someone who's invested 30 years of their life to become an expert at this physical way of measurement, and suddenly tomorrow they find that there is this mental way to like do all these measurements, I think it's a big blow. Like any human would feel threatened. It could just be that.
That I totally agree with. Which is there with scientists. Scientists can get very arrogant. Also, the most brilliant minds are usually extremely arrogant about their theories and their things, but they also, the way they think is very different. I have a lot of respect for them, but there are some things I don't like about their ideologies as to when they kind of shun some things. This is just, I have nothing against them, but this is how I think about things personally. So that's why I don't like to demean astrology completely.
Ramanujan must have faced the same issue.
He
came up with some proofs, like without knowing,
results,
without knowing the process, right?
He just said that Devi came to me and the goddess came to me and said this things. So
no one would believe him.
No one would believe him. Exactly. It's just a different way. That's the thing. It's a different way of expressing the peak potential which you can reach. So for Ramanujan, being from an orthodox family, for him doing those regular things as being from an orthodox Brahmin family, doing all those things, doing puja, all those things, that's what I feel probably helped him become a greater person and a more conscious person, which eventually reflected in his mathematics.
I've been to that temple.
You've been to the temple? Oh, nice.
And I prayed for good marks in my math exam.
How did you perform?
Yeah, it was pretty good. Are we all good?
How do you name the objects in space?
So for me, Pulsars, it's a very shitty way of naming. It's just the orient declination. So, for example, a pulsar is named as J 1925 minus 2526, which means 1925 means it's 19 hours 25 minutes. So we have hours, so it's an hour, 24 hours. So 19 hours 25 minutes and minus 2526, which is basically declination wise, it's 25 degrees 26 minutes. And J is to do with J name, which is the fact that the Earth is precessing. Earth completes a complete precession. Earth is actually precessing. It's not just going this way. It's not just rotating on one axis. This axis itself is precessing. And that happens once every 23,000 years. So the North Star, Dhruva, won't be the North Star always. So because of that, we need to have every 50 years a new reference. And that's what the J denotes. J is for 2000. So J 2000, from 2000 onwards, you have a particular reference, and then with respect to that, you say the orient declination. There was something called B. We also named pulsars as B something. There were pulsars discovered before 2000, and they were with the reference of 1950 because there the North Star is slightly, the axis is slightly off. So with respect to that reference, you have a different orient declination. I know it's very slight, but it makes a big difference because if you have to point your telescopes, you need to know the exact position as precisely as possible. If we know the position as precisely as possible, you can collect as much light as possible from that source. Because if you're slightly off, you'll get background radiation as well, which is not good.
What is something that is so counterintuitive about space that most people don't know about or they just assume? Do you have something to do?
Whoa, okay.
It's like something which in our day-to-day life we just take for granted, like this is how it is, but if you look at the physics behind it, it's like completely... I think one thing for me was like gravity is not a force.
Because it's just a curvature in space of time. I think that's one of the good examples. Apart from that, something counterintuitive.
Nothing coming to your mind.
Nothing coming to my mind as such. It's just that I think I've been in this field so much that I think anything which is counterintuitive also is kind of an, I was expecting this.
Yeah. You've gone too far to the dark side. Okay. No.
But yeah, I think there are definitely there are things like, for example, just the fact that when we just look at each other, I think cosmology is very counterintuitive because we just look at things here, we just look at how things are, and to know that the universe is expanding and actually accelerating, and also the fact that we are rotating, revolving, and our sun itself, the solar system itself, is revolving around a galaxy. Motion is happening everywhere, but still we feel stagnant. I know the physics of it is very simple to explain why we feel that. It's just that the velocity is almost constant, and our bodies tend to are sensitive only to acceleration and not to velocity. So, but it's still, I find it counterintuitive that we feel like there's nothing happening, but there's actually so much happening. I mean, the other thing is that you go from here, from Earth, you expand to a solar system, you expand more, and the amazing thing is we know what we don't know. Also, we don't know what we don't know. That's what really fascinates me about this field, because at some point we are just limited by the fact that speed of light is finite. So there's a lot of things which have just not reached us or cannot reach us because the speed of light is limited. That really fascinates me. It's counterintuitive. Like, there's a lot which is there, but we just don't know that it's... We don't know, because the only way we get information is through light, which has changed now, by the way, because of gravitational waves. The discovery of
Amazing.
gravitational waves. That was a great discovery. Yeah.
Which is faster than light?
No, it's the same speed of light.
Okay.
But it's a different way of getting information.
Okay.
All our information used to be light. When I mean light, basically the entire spectrum, from gamma rays to radio.
Okay.
Everything used to be in this. But now we have a different way of getting information. It's through gravity waves. Basically, changes in space.
That was when that proved that the universe sort of just it compacted and expanded a little bit when that gravity.
So what happened is when the two black holes merged, it kind of caused a ripple in space and time. So it just changed. So if you think of space-time as a fabric, it caused like a perturbation in that. And from Einstein's theories, we realized that space and time are actually very much related. They're not separate things like how it is in Newton. In Newton's theories, we treat time as an absolute thing and very separately. But then Einstein came and said that no, time influences space, space influences time. So what happened here is,
just like electricity and magnetism.
Yes. So light bends. So one of the things which immediately came to Einstein's mind was an object can bend light. And this is a hot topic of research in astronomy. It's called lensing. It's called gravitational lensing.
Did they verify that with one of the eclipses?
Okay, I'm glad that you brought that up. So what happened was, again, a very interesting story. What happened was, should I just tell the entire Einstein story? Or I think it's already there on the internet. Okay, maybe I'll just tell the highlights of it. In 1907, actually 1905, Einstein published these 4 papers. The special theory of relativity, Brownian motion, photoelectric effect. And there were 2 papers on special theory. The other one was the E equals mc square, which had that formula. So he had these 4 papers, and then
while he was working as a clerk.
Yes, right? he was a clerk in a patent office in Bonn in Switzerland, and in his pastime he was doing this. He was also taking help from his friend who was a mathematician. I forgot his name, and he was doing this, and then he came up with these 4 papers. Max Planck got very impressed by his work, and then he became famous after that. But one thing which intrigued Einstein was that gravity doesn't fit in this theory of his. So his next aim for the next 8 years or so was to integrate gravity into his theory. And for that he needed to learn the math of it. So it took, after 8 gruesome years, he eventually published it. But what happened is in 1914 itself, he had a theory. Like he thought he had solved it and he had some formula, and he expected from that that light is that the sun is going to bend the light coming from a star which is behind the sun. So let's say we are looking at a particular region of the sky, we see the starlight, and then the sun comes there, and that starlight is going to be slightly perturbed because light bends gravity bends light. Oh shit! I kept saying light bends gravity. Gravity bends light.
Yeah.
So what happened was 1914. He one of his there was an apprentice of his who decided to go to Russia and observe the eclipse. So in 1914, a total solar eclipse was going to happen, and they were going to make measurements just to verify if Einstein's theory is right or not. And the day they went, the First World War broke out. It was in 1914. So the Russian police caught them, and somehow Einstein, using his influence, he could get them back. Luckily, they were caught for a while, but then he brought them back. But then, as he kept looking at his theory, he realized he had made a mistake. He had made a big blunder, and the calculation eventually, he had predicted that in the calculation that the amount of change which happens because of the light bending was a factor of 2 different. When he corrected for the error, he had made a factor of 2 error. So then in 1919, eventually Sir Arthur Eddington went to Africa, one of the islands in Africa, and then he observed the total solar eclipse there, and then he realized that the calculation made sense with the measurements, and then he became an overnight star. So in a way, the First World War breaking out was a boon for him.
But he won the Nobel Prize because of his photoelectric.
Yes, that is a political thing. That is a very political thing as to why he won it for the photoelectric effect and not for the theory of relativity, because he was a Jew and he had fled Germany, and there were some scientists who were against him. And so there's someone who comes to my mind is Philip Leonard. So he was the one who developed the cathode ray tube, and he was particularly against Einstein, and he had created a bad image among the Prussian society that Einstein, being a Jew, his theories, these are Jewish theories which are bullshit and maybe they don't make sense and all that. But at one point after the eclipse, he became, his photo came on the Time magazine and everything, so he became an overnight star. And then eventually what happened was they realized that they can't ignore Einstein, and but still they thought they'll instead give it for the photoelectric effect rather than... It was a political thing as to why he didn't get it for relativity.
But so my other maybe dumb question which I realized, so they had to wait for the eclipse because you cannot observe the light of the star when that's...
He said first they observe before and then the eclipse happens.
Yeah.
So when the eclipse happens and then the starlight from behind you...
It's only the starlight that
exactly.
you pick.
Basically it's just to do with brightness. You can't see any of the other stars in daylight. So, but when the eclipse happens, you can see those stars behind. That's all. It's just a simple concept.
The other section that we wanted to get into was like some of the practical aspects of like astrophysics.
Yes.
Which was like, one question I had is, I'm working a little bit with machine learning.
Yes.
And how is this being... You mentioned that you were also working on this thing. So any particularly like disruptive applications of like machine learning with astrophysics?
Yes. So I can speak about my own problem. So what has happened now is our we have certain algorithms, signal processing algorithms, to detect periodic signals from the radio data. So I told you that these signals are periodic. So we use some clever techniques using the fast Fourier transform, and then we do some signal processing on that. A lot of other things trying to take care of the fact that pulsars have the so and so properties. So we exploit that and we incorporate that in our algorithms, and we try to see if we have discovered a pulsar or not. So what happens is we eventually when we take the data, we reduce them into data cubes, which are a much reduced form of the raw data, after applying all these algorithms. And these data cubes, we have visual plotting tools, which plot projections of these data cubes, which by human eye, we try to say if it's a pulsar or not. So there are certain things we expect from a pulsar signal, that it's going to be persistent in time, persistent across a large range of frequencies and those things. And we plot these projections and we make an estimate that, hey, probably, yeah, this data cube, this is a pulsar. Now what happens is, because in surveys before, the kind of these data cubes which were produced used to be hundreds to thousands. So you would just manually go through them and say it's fine. Now we are dealing with millions, and we're going to be touching a billion soon with the number of these kind of data candidates which are coming. And it's humanly impossible to go through millions of candidates in good time. And enter machine learning for us. This is where we use our knowledge from previous candidate data cubes. We have labeled all of them, saying ones, let's say, a very simple thing, ones and zeros. This is a pulsar, this is not a pulsar. Ones and zeros. You have a labeled data set, you use it as a training candidate data set, you develop a neural net on that, and then you use the test data set to see if you discover pulsars. And in fact, these trained models have been applied on previous data sets, and pulsars have been discovered, which have been missed by the human eye. Because the humans, it depends on what time of the day you are probably looking at the candidate plot. Humans will get bored of, maybe I'm just seeing too much of noise, maybe this is also noise, and you might just end up in a false negative. This is what we call a false negative. Basically, we are trying to reduce false negatives. We are trying to make sure that if there is a pulsar, we catch it. We are okay with having more false positives, but as long as false negatives are less. So, because we are okay with dealing with more crappy data cubes, but we want to make sure that if there are pulsars there, we definitely catch them. So that's how our problem is. Of course, I think different fields have their would focus on false positives more than false negatives. But my problem is in my field is that in pulsar searching, when we are doing all these algorithms, we have these data cubes. We are trying to use clever models and trying to see if we are able to discover pulsars which are in a faster way, and also which are probably missed by the human eye just because of negligence. Because a trained model can never get bored of looking at data, but humans can get bored.
Have you used any unsupervised learning on data? Like
That's
clustering
a good question.
on some...
That's a very good question. This is something we wanted to do because in my field we haven't done it. But the thing is, there are some intricacies of the candidate data cubes which we produce, which we feel that it's probably not worth investigating so much into unsupervised learning.
Okay.
So, for example, we expect certain properties of the data cube, which we take care of before. Now, what happens is in unsupervised learning, you're just giving the whole raw data, and you're trying to make it figure out things on its own. I think for something like noise, and actually when I mean noise, we also have another thing. It could be noise, it could also be something called as RFI. We call it RFI, which is radio frequency interference. A big issue with a lot of our telescopes is that they overlap with mobile bands, which will corrupt our data. So radio astronomy, we hate mobile phones. But unfortunately, we are a very small community, so we can't really influence. But there are certain bands which are protected for radio astronomy, like the 1.4 gigahertz band. So 1420 megahertz is a very important frequency in radio astronomy because that is the transition between, so if you had studied some quantum mechanics, this is a transition between the two states of hydrogen. One where it's...
okay, thank God.
So it's 1420 megahertz, and you see this literally everywhere in most of the sources when you're doing radio astronomy. And it is used as a probe to study galaxies itself. And sometimes it's used to study things which are in the background. You can do all kinds of amazing things with just by using this H1 radiation, which we call it H1. So this particular band for example, is protected for radio astronomy. So, but unfortunately, for pulsars, we try to observe in a lot of bands. So we are corrupted by terrestrial signals. So many times we get signals which look like pulsars, which are actually terrestrial, and we want to make sure that we don't. That's where the false positive happens. So
and it must be everywhere, no? This
it happens a lot. It happens a lot.
It's like an annoying stalker. Or
It's
something.
exactly. It's just so. We have this terminology called birdie, which is basically this well-known frequency which is always literally there in your data, and which is just corrupting all the data.
Yeah.
So we try to remove those particular data and try to find if we are able to see the pulsar in the rest of the data. But the problem is, if you're removing a chunk of it, we lose sensitivity. We are not able to get the whole data set, and if it's very faint, it would be nice to have everything, and then we would actually be able to see if there is something. Basically, signal to noise ratio. We want to improve on the signal to noise ratio. So these things can really affect us.
So the other question that I want to ask you is, what is your view on Starlink? So obviously you're...
You mean the probe which is being sent to Proxima?
No. The Elon Musk's constellation Starlink. 60,000 satellites orbiting Earth. I think the only option for you guys is to go into orbital telescope, because there's nothing.
This was discussed about a week back. We had this discussion. It's going to be a pain. So what we are going to do as radio astronomers is we are going to come up with a system where, let's say we are tracking with our telescope. We're going somewhere, and we know specific details about these satellites as to how they're orbiting, at what time of the day, where they're going to be. The moment they come within our beam, we just stop observing for a while.
That's sad.
Yeah, I mean, it's a sad thing, but unfortunately, that's how we have to deal with it.
It will provide you high-speed internet. So.
This is where it would be nice. Maybe the good thing would be to have a base in Moon to do things, and even of course, actually, if you want to detect gravitational waves. I don't know if you guys have heard of LIGO. LIGO is the one which is in the US, which have detected all the gravitational waves so far. But we can also have a space interferometer, where you basically have an interferometer in space. You're trying to. It's just a conceptual thing right now, but it would that takes care of a lot of issues. Especially with RFI, with false signals, that's one thing. And also, we will be sensitive to, just like how in light you have multiple wavelengths, in gravitational waves also you have multiple wavelengths. And let me advertise my field again. Pulsars can be used to detect gravitational waves.
Okay.
So what happens is, I told you about these periodic signals, and the amazing thing is the periodicity is so good that you can precisely predict when the next pulse is going to come. So for example, for all our clocks, we use atomic clocks as standards because of their stability. Apart from, let's say, a cesium atom or a hydrogen maser, which is what is used now in clock standards, if you want a very precise clock apart from these two, I would say pulsars are good clocks. That's the amazing thing. It's something in space, but just by timing them, you're able to keep a good precision of time. Now, what happens is, if we know everything completely about the pulsar, take care of things like we are moving, revolving, so there'll be an annual variation, you demodulate that part. Sometimes they might have some bizarre behavior, you take care of all those things. So what you would expect is, across time, you're going to get, you will predict that the difference between what we observe and what we expect is going to be zero. And that's going to be constant with time. Now let's say a gravitational wave passes through. It's going to change things. And there'll be a change.
Okay.
Which will be the only cause of it.
Awesome.
Yes.
So you said
Pulsars are awesome, man. Pulsars are awesome.
That would be another comment.
You said that there is a lot of noise on Earth for astrophysicists. right? There is
It's basically interference.
yeah.
Radio
So there is
frequency
an
interference.
incentive for astrophysicists to go in space or on moon.
Yes.
Yeah,
and
I think that'll be the
definitely.
only option.
Definitely. It's basically it's about money.
So be astronauts.
No, you can like remote use a telescope or a base that is.
Of course, that's fine, but how you can't achieve a lot by just doing remote things. Sometimes it's important to have humans there for
on the spot.
exactly.
Okay.
So are there any astrophysicists who became astronauts just to do this research in space or International Space Station maybe?
As far as I know, no. I think a lot of astronauts become astrophysicists because when you're an astronaut, you're basically trained physically, mentally, everything, and so I think it's an easier way to go from an astronaut to an astrophysicist than from an astrophysicist to an astronaut. Maybe many of the astrophysicists are just not so physically fit, and that's why they couldn't become astronauts.
Yeah.
So, yeah, astronaut is a totally different ball game. I mean, you're supposed to be. For an astronaut, I would say having an engineering background is better because you need to fix things.
Yes. Have you seen Chris
like a
Hadfield's
maintenance.
Chris Hadfield's TED talk?
No, I don't think I've seen
he was on a spacewalk and he went blind
Okay.
because sweat dripped into his eye or something like that, and he had to like do other stuff to like get back to this thing. Like amazing.
Oh, okay. I should
Yeah.
check this.
The other question that we wanted to know about was like funding
Yes.
for these astrophysics, which I think I was also telling you while we met. Is I feel it's heavily underfunded. But what is like? How do you? What's the? Who funds you? Where does the money come from? What can be done more?
So particularly for me, where I'm working, this is from the Max Planck Society itself. So Max Planck Society is a conglomerate of 80 institutes in Germany, and they have their own funding, and basically the German government allocates a particular amount to the Max Planck Society always, and then of course through their own research they're able to get grants sometimes. So one thing which happens is, which you would have definitely noticed when the black hole image came out, I think it made news everywhere, was people kept saying so the Europeans kept saying the Europeans played a big role in this, and the US people said US people played a big role in this, and then everyone. So that is kind of the state of how funding is in astronomy. It kind of sums it up, because you are trying to do research, you're trying to market your research just so that you're able to get more funding, which is kind of a sad state right now. Also, I do understand why astronomy is not funded that well, because it's one of the fundamental sciences. It doesn't have too many repercussions for society as such, which I understand. I totally agree with that, because these are the fundamental sciences, and things like astronomy, these are something which you pursue as maybe as an interest out of just great passion and to know things and such things. But if you want to solve problems about things on Earth, your astronomy is not really the in fact it's the exact opposite of that. So that's why I think astronomy is not so well funded. But all I would say is that I think every country should, of course, they have their own problems. Many countries are underdeveloped. They have issues of poverty and education to deal with, of course. But once they are able to cross these barriers, let's say, I feel that, or even like developing countries like India, for example, people should start investing in fundamental physics or fundamental science, because it definitely has long-term repercussions, which of course you might not see in your lifetime, but it definitely, for the welfare of your own country, it's definitely a good step. Of course, with the way world politics is played out right now, I think many countries are heavily invested in military and just protecting themselves and all these things. Of course, if, for example, just look at the EU. I mean, look at how the EU was formed. After the World War, all the countries realized that there's no point fighting. Let's just make one union of all the European countries, and then it would just make more sense. And monetary, I mean, even in terms of monetary benefits and everything else, social welfare, everyone would be benefited. Which I think was a great idea. So someday when there is an egalitarian society where the whole world is one, which I think we are far away from, given that politically I think we are just, it's not really going that way. But I feel once you're able to take care of these very basic problems, once you're able to take care of basic food, shelter and clothing problems for and education, these kind of things. These are very vital things, which I don't deny that they should be invested in. But once all these things are taken care of, I think it's very important to invest in fundamental science. Because, so I, specifically with astronomy, I can give you an example. Astronomy has implications on technology, and technology has implications on astronomy. So there's this very nice article, which I'll probably share with all of you, and maybe I can put a link as well. So one of the things is that when charge coupled device was invented, for example, as part of in electronics research, it found its way into astronomy, and it's heavily used now in astronomy for imaging. So astronomy has benefited a lot from technology, but it's also the other way. Now, when NASA has to take care of how environments in which astronauts have to be in, they came up with this concept of clean rooms, where basically, so that astronauts are, you simulate an environment where astronauts are as if in a place where there's no gravity. That's one thing, but also they have to deal with things where you have to be very careful. It's very necessary to be in a clean room and these kind of things. So also the material science wise, you need materials which make sure that you're fine in space, and all these have found applications in day-to-day lives. I mean, clean rooms are used now in hospitals. The technique of interferometry, which is a technique where, this is something I didn't speak about. So let's say you have one single radio telescope observing and you can get some signals. It would also be nice if you have a collection of dishes and together they work as if it's one telescope. The amazing thing is you get better resolution, but you also get more signal. So there was a Nobel Prize which was given for developing a technique where all these telescopes can work together and create an image, which is called radio interferometry. This was a technique developed in the 60s, and this was actually expanded to what is known as the VLBI, which is very long baseline interferometry, which is what created the black hole image. It was there was not one telescope which took that image. It was impossible for one telescope to create that image, because you're looking so far and you need to resolve the object so fine. So you need telescopes all across the Earth so that you're able to get that finite resolution. So all of them work together as one big telescope, and you're also able to get a finite resolution. So this technique has been used now in MRI scans to create basically images of, let's say, because the same technique, it's basically a Fourier transform. It's a spatial Fourier transform, which is the same thing which is happening here. You're doing a Fourier transform and you're trying to analyze the image. So, and if you ask anyone, will they say, this MRI scan, oh, this is amazing. No one will say that it came from astronomy. No one would know that as well. Yeah. But that's the thing. You have to invest in fundamental science, because there are things in fundamental science, because it's so abstract, so vast. If you start doing things in it, you realize things, and somehow some things will have repercussions in some engineering field or something very practical. Let me take another very basic example. Farmers, it would be nice for them to know that when can they expect rains, for example, right? So, for example, let's say in India, ISRO has launched a weather monitoring satellite, which can help farmers to accordingly prepare for the season of cultivating crops, or accordingly change their plans or some things. Now, how do you think these satellites are working? They are using Einstein's equations. They're using the fact that space and time are related. The gravity on Earth is very different from the gravity in space, and that makes a big difference in the calculations as to where exactly are the clouds moving and those things. Because even with your GPS, for example, you are using special theory of relativity to make sure that, because if you're here, if you're 10 meters above, it's slightly different than here because gravity influences time. That's what we learned from Einstein's theory. So, can you imagine Einstein, when he came up with theory of relativity, do you think that would have helped? Who would have thought at that point that it could help farmers in crop management? But that's the thing, that's the amazing thing about fundamental science, that it's very important that you think in this way, that you have a broad mind, that you invest in things which can really open up the kind of possibilities and applications which are there in all fields. So these are just some examples I'm giving about astronomy. There are a lot of other things. Yeah, I mean, maybe I've made my point here, but yeah. So this is what I feel. Yeah.
So, but in Germany it comes from the taxpayers.
Yes.
Yeah. Okay, so moving on to maybe something lighter, and this thing is aliens.
Yes. Yes. Yes.
Okay, first of all, do you believe they exist, or?
So I think there is a possibility. Yes. Mm-hmm.
Yeah.
So
we're too big to be alone.
Exactly. So we have found another very amazing hot topic now is exoplanets, which is trying to find planets orbiting stars which are in our galaxy. I think we have achieved significantly a lot. This field is very new. It started in the 90s. And in fact, again, I'm going to advertise my work. The first exoplanet was found orbiting a pulsar.
Okay. What is an exoplanet again?
Exoplanet is basically, exo. So exo is something outside our solar system.
Okay.
Basically, it's a planet orbiting a star.
Okay.
In our Milky Way somewhere.
Okay.
So we're trying to find more of these exoplanets. So the aim of exoplanets mainly is to find planets which are Earth-like and which could possibly have life-bringing molecules, organic molecules.
Mm-hmm.
So the way you would approach aliens is first look at ourselves. How did we come into being? Earth had certain conditions. It became something else. Then there were organic molecules which evolved into plants, and then there was evolution which took over and all these things. So you try to use this model and you try to say, hey, okay, let's say I'm trying to look somewhere. I'm trying to expect life somewhere. I look at a star. First thing is I probably find a planet. I try to see how distant it is from the star and try to approximately calculate what temperature it is at. Is it at a temperature where we could exist? Okay, that's a good thing. That's a checkpoint. Good. Next, does it have an atmosphere? If it has an atmosphere, it definitely has molecules. So then you do spectroscopy on that particular planet and see what kind of molecules you have. Do you see carbon-based molecules? They're carbon-based molecules. There is oxygen. Possibly there could be something there. So, but this is what exoplanet research has achieved so far, where we are trying to find a lot of planets and trying to see how Earth-like they are. Are they in the right conditions to harness life, to have life? But of course, we haven't seen life as such yet. But I feel that it's just a matter of time. It's just a matter of time. Of course, I also believe that there could be more intelligent species than us. And I think this idea for me personally, it's more influenced from Neil deGrasse Tyson, because he just made this very simple comment that the difference in DNA between us and monkeys is just less than 1%. And if we are supposed to be more intelligent than monkeys, then what are the odds that there's a species which is slightly 1% different from us, and that they're much more intelligent than us. It's very much possible. And that's why I feel in terms of research-wise, we are definitely getting there. I think we are going to find microbes first, probably. There is also a very nice field called Panspermia, which is basically the fact that...
I actually had written it in one
Oh,
of my
okay.
books. Yeah.
Okay, yeah. So the fact that life originated on Earth because of molecules coming from outside.
Because during the formation of the Earth, it
Yes.
was too hot
Yes.
for any life to exist.
Exactly.
And then it took several million years for everything to cool down, and then still there was no water. Water is very liquid water
It's
is
very
very
essential.
essential for life to happen.
Essentially, yeah. This is still a hot topic, but this is a very interesting topic as well.
Yeah.
And of course, there are evidences for and against it, but I'm not the expert in this. I just know it
No,
as a term.
from
Yeah.
this thing,
Yeah.
like common sense perspective, it's like it's just like a hot molten piece of rock. Then it cooled down. Still, there was nothing organic like carbon,
Exactly.
hydrogen, oxygen. There was nothing like that over there. It was like some rocks.
Also, there is a theory. There's a very strong theory that there was a collision between Moon and Earth,
Yeah.
which could also have possibly caused something. So,
But is it possible? I mean, this is just a random idea I had right now. That maybe there exist other life forms that
Yeah.
don't need oxygen.
yes,
So like we could be like looking
Yes.
completely. Maybe in another system they've
Exactly.
evolved to like breathe on hydrogen.
sure,
Who knows?
sure.
Or
Sure.
don't even need water.
Yeah,
Would that
exactly.
also be
Yeah.
there?
Sure,
Yeah.
that's definitely a possibility. It's just that we know
Yeah,
only as much as what we
exactly.
have.
Yeah.
We know that we need oxygen, we need these things. So, but one thing definitely is we look at our body, and our body is very organic and carbon based. So then we feel that probably carbon is definitely one of the essential molecules. And of course, it's possible. See, we have to start somewhere. It's possible that we are completely way off. It could be magnesium, which is the essence of life somewhere else. It's a possibility.
Yeah.
But we can do as much. I mean, this is where, as I said, we don't know what we don't know, but we can at least start with what we know.
Yeah.
So,
And do you have samples of other planets of the solar system? Like, what is the composition of the?
So when Apollo 11 they had gone, when Armstrong and others they went, they brought back samples from the moon, which are still being studied, by the way. There's a very nice video. It's a YouTube link. Basically, they show. Oh, I think it's Veritasium.
Yeah.
I think you all know Veritasium, right?
I know it.
Oh, okay.
Physics girl or Veritasium? One of
The Veritasium,
Yeah,
not the
Veritasium.
physics school, the Veritasium. So he goes to the center where moon samples have been stored, and they're still being studied for composition. Basically, they're doing a lot of spectroscopy, trying to understand the composition of molecules, and they're trying to see if this is the composition, then okay, what can cause this composition? Is there some correlation between what is found on Earth? And that actually gives some clues as to if there's some kind of interaction which happened between Moon and Earth, for example.
So it's not the same elements that are on Earth. Is it completely different?
As far as I know, I think it's a lot of silicates, a lot of I think there are some minerals which are common with Earth, but I'm sorry, I don't know the exact details. I don't know what other molecules are. I think carbon, I'm not sure. Definitely silicon and silicates, I think they're definitely found. Yeah, this is just sand and mud, so
Yeah.
this is, yeah.
Have you heard of Bob Lazar? This guy?
Oh, Lazar. No.
He was a Area 51 whistleblower. So, yeah, I know there are a lot of crazy stuff around him, but this guy came on Joe Rogan's podcast, and they made a documentary on him and all of that.
Okay.
And he was claiming stuff of like he has seen spaceships which create their own gravity fields. And he said that it runs on some deuterium or some isotope which doesn't exist on like Earth, or element 116 or something. I don't know. Moscovium or something like that. Which on Earth we have only managed to create an unstable isotope, but that machine runs on like a stable. So he was claiming all of that. It was, I mean, just to listen to him as just possibilities, it was quite fantastic. Is what he was saying.
It quenched the fantasy aspect of life that we so desire.
But it's always, I think sci-fi is actually good, because I think 100 years ago, who would have thought that we'd have a computer in our pocket? That was fantasy 100 years ago. So it's definitely a possibility, whatever we think of fantasy now. And yeah, I mean, I'm definitely.
Here.
But you should watch that interview with Bob Lazar.
Yeah, I think I'll watch it. There is a lot of things to do actually now. I'll have to keep a note of things now.
But you don't have samples from other planets? No?
Mars. I think Mars, I think, of course, rover has done a lot of studies there, but I'm not sure if there are samples from Mars. But everything else...
I don't think anything has come back from Mars.
No.
Yeah.
Because it's very difficult to going there itself is a big deal. So, so I think Moon is the only one which really have samples on. So everything else is basically based on spectroscopy.
Mm-hmm.
We try to study.
And with spectroscopy, you can only study what's on the surface, not inside.
Exactly. Yeah. This is where if you use different observing frequencies, you can probe. You just use the same concept.
Mm-hmm.
So on the Earth, you know that this frequency will go through.
Okay.
So you use the same thing there. Depending on what the atmosphere is there, you try to come up with which frequency would be good for that.
Mm-hmm.
Of course, if there have been a lot of missions which have gone there and imaged, and they have their own set of equipment, so just to make sure that you're able to probe the entire depth of things. So yeah, it's a very fascinating topic, but yeah, spectroscopy is extremely powerful. Very underrated, but extremely powerful. Yeah.
All right. We talked a lot about sophisticated stuff.
Yes.
We are coming to the end of our podcast now.
Oh, okay.
Yes, and now I have a very few basic, simple questions.
Sure.
And I would just like to know your perspective on it.
Sure.
For example, I think that it would be very difficult for you to get mad at the menial things. I mean, the stuff that happens around you, the frustrating stuff happens around you because you are used to look at things at a very large scale, on a big, huge
That's
scale.
not true. That's not true. I know people have this perception about people who do astronomy. You look at things outside and you forget about...
Yeah, I mean,
it's basically that quote from Carl Sagan. I mean, we're not always thinking about that thing.
And it's also, I think, partly because a lot of the social media have this photo of Milky Way with this arrow saying you are here.
Yeah, exactly. It's nothing like that. We are all human beings. We are all normal. We all get frustrated. Yeah, as I said, on a day-to-day basis, I'm debugging. I'm coding. So
if he doesn't get frustrated, we have found aliens.
Yes.
I just thought like you just had an accident and it was like, that's cool.
No. It would be nice to be like that, but
If the rate of petrol goes up or down, doesn't matter.
Doesn't matter. Donald Trump re-elected doesn't matter. So,
Yes.
what is the most common question that you are asked in parties, for example, apart from like your place or my place conundrum?
Common question. What are you going to do next? What are you going to do next?
This is what every parent asks this.
Exactly, but especially if I'm doing astrophysics, because most of them don't have an idea how this a career in academia.
Astrophysicists don't have an idea.
Don't have an idea in a career in academia, so they're always curious to know, okay, what next? What this? And then they ask these things like, oh, do you just go outside and look at stars? I mean, not directly, but they might. They don't think that we are like just sitting. They definitely don't have an idea that I'm just sitting on a computer and doing data analysis. That's never on their mind. They always feel I'm always hanging around with a telescope, looking at stars. Yeah, but that's not how it is.
All right then. I think we'll bring this episode to an end. Thank you so much for coming,
It was my pleasure. I really enjoyed.
I enjoyed it too.
Enjoyed a lot.
I was blown away. Not just enjoyed, blown away. It makes me want to think like, huh.
Yeah, your blown particles are accelerating.
And I think I can keep talking on this, like asking questions for like ever.
Yeah, I mean, I'm willing to answer them because I think it's been long for me as well. It's a refreshing change for me also because on a day-to-day basis, I'm just sometimes doing very mundane things. It can get boring, but having these kind of conversations helps sometimes rejuvenate yourself and you brings back the drive in you. So that's why I was very eager to have this as well. Yeah, but thank you.
Yes.
It was really nice.
So, yeah. We still haven't figured out how to end.
1, 2, 3, end.
Thank you for listening.
Thank you for listening.
Please like, share, and subscribe.
No. I have made a policy not to tell people. We should do it organically. If they want to share, they should share.
Okay, if you like it, like it. If you want to share,
No, we don't do that. So, unhear whatever you just said. And thank you for.
If you have any questions, note it on the comment section.
Yeah. We can.
Then send Rohit Rao a friend request in Facebook. He doesn't use it. That's why I'm telling you. Switch it off.
Yes. We need to work on this.